So if you want to do physics, one thing you have to always consider is relativity and frames of reference. This isn't to be confused with special relativity, which is a lot of people's first thought when they hear the word relativity. Special relativity only really applies to objects moving at very, very fast speeds, and is a story for another time. So to explain why relativity is so important, imagine you're looking at a ball being launched up into the air from a distance. You can calculate that the ball is being launched with a certain velocity. Simple enough, right? The ball just moves straight up and straight back down. Now, imagine the ball is on a train moving towards the right side of your vision. Now, the ball follows a curved path across your field of view. Granted, this is a little more complicated, but you can still pretty easily figure out the velocity by simply adding the velocity of the ball and the velocity of the train together. Now, however, imagine that your friend is measuring the velocity of the same ball, but they are riding on a car moving in the same direction and at the same speed as the train. Suddenly, from their perspective, the ball is moving straight up and down again. The two of you compare notes and find that you calculated different velocities for the same ball launch. How is this even possible? Nothing that you two did affected the ball launch in any way. The key to understanding what is going on here is understanding that there is no such thing as an absolute velocity. Velocity can always be changed simply by looking at a different frame of reference. If you are sitting on the ground here at Earth, sure, you are staying still, you have zero velocity. However, that is zero velocity relative to the Earth. Earth is your frame of reference, the assumption being that the Earth is staying still. Most of the time, we just assume the Earth is staying still because, well, it looks like it is. But if you set the Sun to be your frame of reference, suddenly the Earth is whizzing through space at quite a fast pace. And if you set the center of the galaxy to be your frame of reference, it's moving even quicker. In fact, you cannot measure the velocity of anything without first asking the question, relative to what? For example, when you run, you're moving at a velocity relative to the ground. But when you run on a treadmill at the same velocity, you're still moving with the same velocity, only now it's relative to the running belt. What the treadmill does is the running belt moves in the opposite direction. So even though you are moving with a velocity relative to the belt, your velocity relative to the ground is zero. So, going back to our ball launch example, from your frame of reference, you are still and the train and the ball on it are moving. But from your friend's frame of reference, the car and the train are both still, while the ground and everything on it is moving in the opposite direction. This is how you two can come to different results on the ball's velocity. So, while it may be simple enough to treat the Earth as fixed in most cases, sometimes more complex problems can be made much simpler by keeping relativity and frames of reference in mind.